Hi, Math 1, Mr. Bruns here again, and today we're going to talk about solving inequalities. We spent a lot of time earlier in the year solving equations, and most of those dealing with just one variable. And today we're going to talk about solving inequalities. These are very similar, but we are going to break them up into a couple of steps. I'll do one example here, and then I'll do another couple of examples in the next video. Let's start with an inequality that looks like this. Inequalities, you may remember, don't have an equal sign, but they might have a greater than or a less than sign. And so our example right now is going to be 5x minus 6 is greater than 3x plus 1. So the first way we want you to solve these, you may have learned to solve these before in some method, but for us, we want to do things a little bit differently than what you may have seen before. And that is, we're going to actually treat this as if it were an equation. Okay, so we're not going to forget about it, but right off the bat, we're just going to rewrite the whole thing as 5x minus 6 equals 3x plus 1. Okay, that looks a lot more familiar to us. We have ways of solving that. We all should be pretty good with that at this point here. I think what I'm going to do is I'm going to send all the x's to the left side. So I'm going to subtract a 3x. So I have a 2x minus 6 equals 1. I'm going to send the minus 6 to the other side. So the way we undo subtracting 6 is we add 6 to both sides. And I have a 2x is equal to 7. And then we want to undo the multiplication of 2. So we're going to divide by 2 on both sides, and so I get x equals 7/2 or 3.5. Okay. What we've just found there is that's the x value that will make these two equations equal to each other. Okay. But we're not actually looking for when they're equal to each other. Remember, the original problem is asking for when are those two, when is this thing greater than the right side? When is the left side greater than the right side? So this point that this x value that has made the two things equal to each other, we call that a boundary point. So this x equals 3/2 is our boundary point, and once we find that, we're going to take a look at a number line. So I just, I have every number I can think of is going to show up on that number line. I'll just put a little 0 here, although I don't need to see 0, but in this case, I don't mind seeing it. And then I've got a 1 and a 2 and a 3 and a 4 and a 5. And hey, right in between 3 and 4 is that point 3.5. Okay, that's my boundary. And basically what's going to happen is we're going to test on either side of that 3.5 to figure out which values will make this a true statement. Are they the values over on this side, or are they values over on this side? Sometimes it's neither, sometimes it's both, but that's our job now, is to test those values. Okay, so I'm going to kind of rewrite all of that so I have a little more room here. Remember, our original inequality was 5x minus 6 is greater than 3x plus 1, and we found a boundary point of x equals 3/2. 0, I'm sorry, not 3/2, 3.5. And so I'm going to test. And one value I'm going to test is something to the left of 3.5. And I'm going to pick an easy to test value. 0 is a really easy to test value. Okay, so I'm going to test. We're going to let x equals 0. And if I let x equals 0 and I go back into that original inequality, this thing right here, I will get 0 minus 6 is greater than 0 plus 1. You got 5 times 0, you got 3 times 0, both of those can be 0. And I say, oh, negative 6 is greater than 1. And the question is that a true statement or not? And is negative 6 greater than 1? No, it's not. So we see, oh, that's a false statement, which means 0 was on the left side of this boundary point. So really, anything to the left of that boundary point gives me a false statement. That's not part of my solution. I'm looking for values that will give me a true statement that will solve this inequality. And if I've done things correctly, if I tried 0 and I got a false statement, if I had tried 1, I should also get a false statement. And if I had tried, say, negative 2, I should have also gotten a false statement. That any x value on the number line to the left of this boundary point right here, any x value to the left of that should have given me a false statement. Okay, all right, so we're going to try the other side just to make sure we didn't make any mistakes here. I'm going to test something to the right of 3.5, and 5 is a pretty easy number for me to plug in. I know how to multiply things by 5 pretty quickly. So I'm going to let x equal 5. If you wanted to try x equal 10 or plug in x equal 100, that's fine. All of those values are to the right of 3.5. So I plug in 5 for my x. I let x equal 5. I got a 5 times 5, so it's going to give me a 25 minus 6 is greater than 3 times 5. That's a 15 plus 1. Let's see, 25 minus 6, that's a 19 is greater than 15 plus 1 is 16. Is 19 greater than 16? Yes, we have a true statement there. That is true, that 19 is greater than 16. And again, if I had tried x equal 10 or x equal 100 or x equal 7, if I'd plugged in any of those other x values that are to the right of 3/2, provided I'm doing things correctly, they all should have given me some sort of a true statement, okay? And so what we found then is on this boundary point, anything to the right of that boundary point is a solution to this inequality. If I go back to a simpler picture, a simpler example, if I just had the equation x equals 3, this is going to be really dumb here, how many x's will make that a true statement? You know, the answer is there's only one of them, 3. If I let x equal 3, I get the equation 3 equals 3. That's true, okay? If I put in 7, does 7 equal 3? No. -4, does -4 equal 3? No. Does 100 equal 3? No. The only thing that will make that true is if 3 is equal to 3. So there's only one solution to that equation. But if I had said x is greater than 3, how many x's would make that a true inequality? And there's lots. I could say 4 is greater than 3. 19 is greater than 3. 22,000 is greater than 3. 18 is greater than 3. Lots and lots and lots of points, lots of x values would make that a true inequality. And so what we're getting here when we solve this is not just a single, 1 or 2 x values that make this true, but just a whole range of them, just a broad number of them. And in this case, how do I, explain all the possible values? Well, I have this boundary point that we found to be 3.5 or 7/2. And what we just did after testing things on this side and this side, we found that it's the values on the right side of it that make this true. And so our solution in this case, now these are just our little examples that I was using to talk about, kind of ignore those right now. Basically, we say, okay, x and 3.5, it looks like all of these points that make this work are to the right of 3.5. That means that x being greater than 3.5 is a way to describe or define all the x values that make this true. Okay, now we'll get into this in the next example here, but do I include, we'll talk about it right now, do I include 3.5? If I let x equal 3.5, if I substitute that in here, what I'm gonna get is something like 4 is greater than 4. Because remember, 3.5 was that boundary point that made the two sides equal to each other. So do I want something that has the same thing on both sides? Do I want 4 is greater than 4? Is it true? Is 4 greater than 4? And the answer is no. So I don't want to actually include that 3.5 in my solution. Okay, so the main things here are step 1. What we did over here is we turned the inequality into an equation. We solved that equation and we got ourselves a boundary point right here, okay, x equals 3.5. And then we tested something on either side of that boundary point. I tried x equals 0, and then I tried x equals 5, and I found out which boundary point made this, or which side of the boundary point made it true, and that was the region that kind of gave us our